A pleasant afternoon to all our distinguished guests here at NISCON 2024. Uh, my name is Juan Glicerio, Manlapaz, and on behalf of all of my co-authors and colleagues here, it is my pleasure to present to you our study entitled Optimal Sizing of Hybrid PEMFC Lithium-Ion Battery Power Systems Using Rule-Based Cycle Charging Algorithm for Telecommunication Base Stations. So shown in this presentation, in this slide, is my outline for the study. First, I'll be discussing the background of the study together with the research design that we used, followed by the results and discussion that we've obtained, and the conclusion that we've gathered in our study. So to begin with, I'll give you some context of what we want to achieve and what we're trying to solve. So of all the innovations in the 21st century, perhaps the most consequential one is the emergence of modern communication technologies. These types of technologies enables us to communicate effectively using digital means. However, such telecommunications base stations, or TBS as I'll now be referring to them now, require continuous operation and uninterrupted functionality. As mentioned earlier, since we rely on these kinds of technologies for our everyday lives, it is crucial for us to develop reliable systems to power our TBSs. These can be achieved through the use of backup power systems, as I will be explaining this slide here, which I will discuss first the currently deployed backup power systems such as lead-acid batteries and diesel generators. While both aforementioned technologies are technologically mature and commonly used, lead-acid batteries and diesel generators have some challenges. Perhaps, if lead-acid batteries are only used, it will only cost around 3 million pesos or 53,000 US dollars per year. And if we're going to use diesel generators, while they're cheap, they require fossil fuels which are more environmentally dangerous, and they require frequent maintenance due to its moving parts and are relatively noisy, as we can attest to that. As such, there are some promising deployed backup power systems that I'll be discussing, and it'll be the focus of our study, hence the lithium-ion battery and the fuel cells. As they have all been steadily gained attention in terms of research and development, as they are a good alternative or a candidate for backup power systems. For example, lithium-ion batteries last longer, which makes it more cost-effective than lead-acid batteries, although I'll have to admit that there'll be a talk later by Dr. Carl Odilio on that regard, so please stay tuned to that. On the other hand, fuel cells are more sustainable because they only require hydrogen and oxygen gas as its requirement. So I'm pretty sure that in our audience, you may heard of fuel cells for the very first time. So basically, fuel cells are electrochemical devices that require hydrogen and fuel gas to produce electricity to the form of water electrolysis, of which the byproduct is water. Hence, it's a more sustainable option for backup power systems. As I mentioned earlier, these traditional backup power systems may be cheap and technologically mature, but suffer from environmental concerns. The alternatives, such as lithium-ion batteries and fuel cells, offer the promise of sustainability, but they are hampered by the faster degradation when subjected to fluctuating power demands, as mentioned by my colleague, Mr. Arvin Esotero. This can be addressed, however, by combining it with lithium-ion batteries. However, such addition includes more cost to an already expensive system. Remember, fuel cells are really expensive. And if you're gonna add more lithium-ion batteries, they're gonna make it more expensive. As such, optimal sizing, along with cost effectiveness and system reliability, needs to be addressed. As such, the solution would be an optimized fuel cell/lithium-ion battery hybrid system, specifically for TBS stations. So the goal now is to optimize the sizing requirements of a hybrid fuel cell lithium-ion battery system for a telecommunication base station using Matlab Simulink, and I'll be discussing each of the components here one by one. First is the fuel cell characteristics. So since fuel cells are considered electrochemical devices, they can be further simplified into their equivalent circuit model. Shown in on the left side are the equations. I'll discuss some parameters such as EOC, which is the open circuit voltage, N stands for the number of cells per module, A stands for the Tafel slope, and I sub 0 is the nominal exchange current. Shown in this slide is the degradation equations of the fuel cell, as we need to consider the fact that fuel cells degrade whenever there is a fluctuating power requirement. And shown in table 1 are the coefficient values used in the model. In this slide shows the battery characteristics. For example, in table 2 shows the open circuit voltage equation, which is really dynamic and involves a lot of parameters as well. And to consider the degradation of the battery, we utilize these equations, and table 3 shows the pre-exponential factors at different C rates. Okay. So shown in this slide is the bus voltage and controller algorithm specifications. So as we seen the system before, it requires a DC bus voltage, and table 4 shows the specifications of that. And table 5 shows the control rules implemented in the power system controller. So basically, the control rules aim to figure out if the bus voltage, V bus, satisfies the following conditions. So for example, if the voltage bus is detected to be lower than the controller low voltage trigger, or VL trigger, and if the current state is off, the next state will be at maximum efficiency. And if the V bus is, same again, if the voltage bus is lower than the low trigger voltage, but the current state is max efficiency, the next state should be in max power, and so on and so on. Okay. Another consideration is the cost and lifetime factors of the system. So table 5 shows the cost and lifetime factors of the fuel cell, the battery, and hydrogen. Okay. So shown here is the results. So fuel cells with power ratings of 3 kilowatt, 4 kilowatt, and 8 kilowatt were selected for the analysis. And the battery capacities are incremented by 1 kilowatt hour, as seen in the x-axis of of figure 4 right here. And figure 4 shows the minimum bus voltage for the 4 kilowatt and 8 kilowatt capacity. Okay? It was observed that the 8 kilowatt system was able to maintain the voltage bus even at a small battery capacity, while the 4 kilowatt system required at least 2 kilowatt hour capacity to satisfy for the minimum bus voltage. As we shown in the previous slide, the previous slides right here, the table 4 is the main basis for the analysis in figure 4 in this slide right here. Okay? So next is the results of the simulation showing the fuel cell power loss. That's from left to right, the fuel cell power loss, the battery capacity loss, and the hydrogen fuel consumption. So the results from the simulations show that the power loss, the battery capacity loss, and hydrogen fuel consumption is greater at smaller battery capacities. Okay? So there's that. The cause of fuel cell degradation can be attributed to the on-off stage or the changing output power as seen from the load, or from the TBS rather. And the cause of the battery capacity loss would be the complete discharge. Okay. Shown here in figure 6 is the overall system cost in a 4-day operation. So figure 6 indicates that a smaller fuel cell system is more cost effective since larger systems are still expensive. Okay? So overall, this indicates that a smaller fuel cell system is more cost effective as well. Okay. So for the main insights in our study is that while larger fuel cells are more efficient and reducing hydrogen consumption, they do not justify their high cost. That's why we need to make sure that small capacity batteries can maintain system stability when paired to a suitably sized fuel cell. Okay. For TBS specifically, a smaller fuel cell system with an optimized battery size is considered to be the most cost-effective in terms of minimizing both fuel cell and fuel cell degradation and hydrogen consumption while maintaining reliability as well. And that concludes my study. Thank you for your time. And before I would end, I would just like to acknowledge all the support from the CIPHER project funded by the Commission on Higher Education, Philippine California Advanced Research Institutes, together with aforementioned affiliations such as the Power Electronics Laboratory, the Laboratory of Electrochemical Engineering, and the University of California, Merced, for their endless support and collaboration. Thank you very much. And I'll open the floor for questions.
Thank you, Mr. Manlapaz. Are there any questions from the audience? Okay, I just have one question. Are the methods used here for the optimization applicable for other kinds of batteries as well? For example, what if we hybridize lead-acid batteries and lithium-ion batteries?
Okay. Thank you for that question. Perhaps the overall method, the overall system used in the study can be used in different battery chemistries. However, it will all be different when it comes to the modeling. So, of course, each battery chemistry have their own different degradation factors, capacity loss mechanisms, and something and so forth. And that would be applicable as well for fuel cell systems as well, because there are also different kinds of fuel cells, not only mentioned by this study as well. So, thank you very much.
Okay, thank you for your answers and your presentation. So if there are no more questions, I would just like to give this certificate of appreciation for Mr. Juan Glicerio Manlapaz for sharing their invaluable insight and work on optimal sizing of hybrid PEMFC lithium-ion battery power systems for telecommunication base stations during the NISCON 2024 conference in Quezon City, signed by Dr. Lou Andrew Trio.